Okay, so we have gases notes. All right, so the first thing I want to mention on here is talk about the units for pressure. We're going to have several different units. You guys are familiar with some of these a little bit, but I want to talk about how we actually do conversions with them and do math with them. If we have a measurement in a certain unit, how do we convert it to a different unit? The first unit I want to talk about is atmospheres. Okay, we abbreviate that as ATM. So that stands for atmospheres. We can also have millimeters of mercury. We can have torr. We can have kPa. And one you're probably most familiar with, which is PSI, okay, pounds per square inch, which really that's what pressure is it's a force over a given area. Pounds per square inch. So if we had 1 PSI, it would be 1 pound of pressure per square inch. All right. Now, so to talk about how these relate to one another, there's 1 atmosphere, so 1 ATM is equal to 760 millimeters of mercury. You guys saw that video, remember, where they had the mercury in a tube, and just when they flipped it over in that bowl of mercury, rather than all the mercury just rushing out of the tube, it stayed up in the tube. And that's because the pressure outside was pushing down on the mercury in the bowl, which was kind of counteracting the pull of gravity and any pressure that would have been inside the tube. And it sat at like 76 centimeters, which would be equivalent to 760 millimeters. So mm is for millimeter, Hg is for the symbol for mercury. All right, millimeters of mercury. And that's the same thing. If you remember, one of the guys involved with that experiment was a guy named Torricelli, and that's equal. Those units are equal to torr. Okay. So 1 atmosphere is equal to 760 millimeters of mercury, which is also equal to 760 torr. All right. 1 atmosphere is also equal, this unit here, by the way, kPa is short for kilopascal, kilopascal. But you can just remember it as kPa. 1 atmosphere is equal to 101.3 kPa. And that's 1 atmosphere is also equal to 14.7 psi. Okay? So those are how they relate to one another. I can say there's 1 atmosphere is equal to 14.7 psi. I can say 1 atmosphere is equal to 760 torr. We can also make for every statements. When we do for every statements, really what we're talking about is a relationship between units. We're really talking about a fraction, which really a fraction is just like a division problem, right? That's all it is. So if I were to write these as fractions, here's some examples of what I could do. I could say that there's 1 atmosphere. There are 1 atmospheres for every 760 millimeters of mercury. This would help me if I ever have to convert between atmospheres and millimeters of mercury. Okay? I can flip it around and say the other way too. I can also say there are 760 millimeters of mercury for every 1 atmosphere. This line in the middle, like I've told you before, really stands for quote unquote for every. You can also think of it as per, not like a cat purrs, but like PER, per. There are 760 millimeters of mercury per 1 atmosphere. Okay. I can match up the other units. I can just pick kPa. There's 101. There are 101.3 kPa per Deviante. Pick another one of those units besides kPa. Which one do you like? PSI. There are 101.3 kPa per 14.7 psi. Maya, pick a unit out of those pressure units. Which ones do you like? Which one do you like? Torr. Okay. There are 760 torr. Brooke, you want to pick another one for me? There are 760 torr per 1 ATM, 1 atmosphere. Pretty simple, right? These are called conversion factors because we can use them to convert from one unit to another. So if I wanted to do a conversion, take your exam review I gave you guys and look at number 25, letter A. 25A. A. So here's how we do these types of problems. 25A says we got to show all work and units required to do these following conversions. So in A, this is what we have to do. It says convert 3,000 millimeters of mercury to kPa. So 3,000 millimeters of mercury, convert that, find out how many kPa that would be. So how many kPa is that? All right. So this is how we do it. You might be able to do some of these in your head, depending on the calculation. You might not. So you got to understand how to set them up. It's a little kind of either you call it maybe factor label or dimensional analysis or something like that. It's the use of units. If you can learn how to cancel units to get new units that you want, this can go a long way. It can be one of the most important science skills that you guys have. Science, math skills, whatever you want to call it. I got really good at this when I was a freshman in college, and it helped me immensely. It was the most valuable thing I had all through college. I took physics. I just learned the units for different types of measurements, and because I knew the units for certain things, I didn't have to memorize any formulas. I knew how to set the problem up. It was amazing. So, this is what you do. Whatever is given to you, like in this case, they tell you there are 3,000 millimeters of mercury. They're saying that. That's given. Okay? Whatever is given to you, you always start the problem with that. Okay? That's the first thing we do. So I'm going to take that 3,000 millimeters of mercury, and I'm going to write it down separate. This is going to be the start of my problem. 3,000, and notice how I always include the units, because that's how I do these problems. I can think of that as being over 1. It's the same thing if I want. I don't have to do that necessarily, but any number in unit or any number over 1 is just that number, right? 5 billion, 500 million, 55 over 1 is still 5 billion, 500 million, 55. Same thing, same number, doesn't matter. The next thing you do is you write times, and then you make a line. Okay? So we write down what's given, that's our start, and then we write times and a line. Now what we're going to do is use our conversion factors. All right, whatever unit I started with, which in this case is millimeters of mercury, I'm going to write that down here. I'm going to leave a little space to the left of it so I can write a number in there afterwards. All right, so take the unit you start with, write it on the bottom under that line that you just drew. Make sure you're following closely. It's little things like this that are super simple, but if you miss a step, everything gets really difficult in a hurry. And as I'm going through this problem, if you have any questions, please answer. The reason why I am the way I am with my teaching philosophy is not so you feel comfortable making jokes or talking to friends. It's so you feel comfortable asking questions without feeling like you're going to be made to feel stupid. I don't want you guys sitting there like, ooh, I have a question, but I don't want to ask it because everybody will look at me funny. Nathan? It is, yep. That's another thing you can call it. Yep. So that unit goes on the bottom that we start with. On the top, I'm going to put the unit I want to find, which in this case is what? kPa. All right? So we put kPa on top. Now what I'm going to do is I'm just going to put in the numbers that I used from my conversions that I just told you up there. Now there were a lot of conversions up there. You don't have to memorize them. They will be on your test. They will be on a handout on the exam. On your Unit 2 test Friday, they'll be on the test. Okay, so you don't have to memorize that. All right? So if we look at kPa, when we did those conversions up there, the number in front of kPa was 101.3. So that's what I'm going to use. All right? So in front of kPa, I'm going to put 101.3. Now you guys have your notes in front of you. What was the number in front of mmHg, millimeters of mercury? 760. So I'm going to put that in front of mmHg. Okay, so all I did was I just walked back through it. I put down what they gave me to start. I wrote times and then a line. I put the unit that I started with on the bottom of this line, and I put the unit that I want to find, kPa, I put that on top. Then I just filled in my conversion numbers from the chart we made earlier in the notes. All right. Now you guys know that if we have a certain thing on top and on bottom, it cancels out. Okay. Now we have something that's the same on top and on bottom now. What is it? mmHg. So what we can do is we can cross that unit out now. Not the number, just the unit we can cross out. Okay? So now the only thing we have in this problem is kPa, which is great. You know why? Because that's what we want to find according to the problem. It says, tell me how many kPa it's going to be. So now we just have to do the math. And to do the math when you have numbers on top, numbers on the bottom, I'm just going to multiply across and get a top answer and a bottom answer. And that's going to be like a fraction or a ratio or even a for every statement. But it's really just going to be a division problem. All right? So if I multiply across the top, I'm going to get 3,000 times 101.3. So 3,000 times 101.3, and that equals 303,900. 303,900. We do have kPa up on top, right? So we should write that down also. Okay? Not done yet, though. I got to multiply across the bottom. Anybody know, without using a calculator, what 1 times 760 is? 760. And if I didn't write that 1 down there to start with, I'd just have 760 on the bottom anyway. So just be 760. All right, so now it's just a division problem. 303,900 divided by 760. So I've already got 303,900 up on the calculator. Divide it by 760. And it comes out to be 399.86848. I'm not going to write all those. I could round off to the tenths place and make it 399.9. I could round off the ones place and just make it 400. I'm just going to make it 400. And those units are still there, kPa. And that's our answer. Okay? That's how we do these problems. You take whatever they give you to start. You take that starting unit and put that on the bottom of your conversion factor. You take your unit you want to find, which I call the target unit, by the way, put that on top. Put the conversion numbers in, multiply across the top, multiply across the bottom, divide at the end. Now, we did sig figs. We talked about sig figs earlier in the year. That stuff was not covered in other chemistry classes. That will not be part of your test or your exam. You don't have to worry about that stuff. But now you are going to be having multiple choice tests and exams. So what's important is if you get a number like that, you might look at the exam and look at the choices and you don't see 399.86 and you're like, oh, what's the answer? All right, so look for the number that's closest to it. So something there and you're looking for which choice, A, B, C, D, E, which one's the right one, and you see 400, that's it. It's not like we're going to put 400, make another choice 399.9, make another one 399.86. That wouldn't be fair. Just find the number that's closest to your answer, your math, okay? All right. So I want to talk about just a couple other things real quick. Um, Talking about gases, and we did an assignment yesterday, CER, where you guys were writing about factors that affect gas pressure. So gases are really spread out, right? They're moving real fast. Because they're all spread out, those particles can be affected by different things. They can be affected by, say, the amount of volume, the amount of space that they have to move around in. They can be affected by external pressure pushing on them. They can be affected by temperature. All right, those are some of the factors. Maybe we added a certain amount of gas to affect the pressure, or remove some of the gas to affect the pressure. There's different factors involved. So when we talk about gases in science, it's important to establish a standard environment in which we're acting with these gases. Okay, so we call that standard temperature and pressure. Okay, we don't want to write that all the time though. Be a pain in the butt. So we call it STP. Stands for STP stands for Stone Temple Pilots, one of the best bands to ever exist. Seen them in concert like 20 times. It also stands for standard temperature and pressure. So these are the standard conditions when we're talking about a gas. These are the standard conditions. The standard temperature, really easy to remember this, is 0 degrees Celsius. That's what we consider to be the standard temperature, 0 degrees Celsius. And the standard pressure, to be like the normal pressure, is just 1 atmosphere. 1 atmosphere, that's like our normal pressure that's on us, about. You know, it can change depending on where you're at. But by the way, in PSI, pounds per square inch, when we looked at that, 1 atmosphere was equal to 14.7 pounds per square inch. So that means at any given time, the pressure that's pushing on us on every square inch of our skin is about like having 14.7 pounds on it. If you had like a metal bar that weighed 14.7 pounds and you put it on your hand, you kind of get a feeling of what that would be like. Of course, that would then be twice what you normally feel. But all right, so that's that. Now the thing is, we're going to be dealing with these things called gas laws. Some of the terms I told you to mark for Unit 2 called Charles Law, and Boyle's Law, and Gay-Lussac's Law. Those are gas laws that basically allow us to do math. So if we figure out we're dealing with a certain gas in a certain type of container, what would happen if I changed the temperature of it? What would happen if I changed the volume of it or the pressure or whatever? Um, and what we got to do is whenever we do those types of problems, we got to use a different temperature scale, which is Kelvin. Okay, remember us talking about Kelvin a little bit, right? I want to make sure that you guys can also do temperature conversions between degrees Celsius and Kelvin. You're going to have to do that on the test. You're going to have to do that on the exam. Well, it's really easy to do. All you got to do is take, so Kelvin equals, Kelvin we usually just put K. Remember, it's not degrees K, it's just K. All we got to do is take the Celsius temperature and add 273.15. And that will tell us the Kelvin temperature. Okay? So when we do gas law problems, whenever you're doing math involving temperature, it's just safe to say make sure it's in K. Safe to say it's in K. So if I give you temperatures in Celsius, make sure that you're using Kelvin, which means you got to convert it. Everybody got that? Now this Kelvin scale is meant to go along with energy, with the kinetic energy. Remember that kinetic energy is moving energy. Um, Temperature is really just a measure of the average kinetic energy. It's a measure of the average speed of the particles, right? You remember all this? Okay, so what it's supposed to say is that it's based off Celsius. So if particles continue to slow as they lose energy, as we remove energy from the particles, they move slower and slower. So if they're a gas, move slower and slower, become a liquid, and a little closer together. Continue to cool a liquid, they're going to get even closer and closer until they're all lined up and just vibrating, which we call a solid. We could continue to remove energy and they'd start vibrating even slower and slower and slower and slower and slower until theoretically they would stop. That temperature is called absolute zero. That was one of your terms I told you to mark, right? It's the lowest possible temperature. You can't go any lower than that. And so that temperature is actually negative 273.15 degrees Celsius. Okay? It's about negative 273.15 degrees Celsius. That's where the particles should theoretically stop moving altogether and not have any energy. Okay? Coldest possible temperature you can have. We've gotten very close to that number. Never got actually to it. Don't know that we really can, because even just trying to measure the particles, measure their temperature, measure their average kinetic energy, just trying to measure that, we might add energy, which then makes them move again. All right, so that's why Kelvin is 273.15 higher, because if we add 273.15 to negative 273.15, we get 0 Kelvin. Absolute zero. So that's why we use the Kelvin scale with our gas law math and stuff, which we'll talk about tomorrow, because there will never be any negative numbers. Okay, we won't have to deal with any negative numbers, which is nice. Okay. So we have a few minutes left. What I'd like you guys to do with your last few minutes is I would like you to go back to number 25. I want you all to try to do while I'm here, and we can look at it, and we can make sure we all got the same answers and the same setup. I want you to try to do number 25B. 25B. Okay? And that's it.